Okay, let's get started. So are there any questions from last time, from yesterday? So the attendance sheet is being passed around. Please work on your handwriting. So I've taken the liberty of writing a program to generate the list on there, so all you have to do is fill in a box. You don't have to write your name or anything. So it'll be a lot easier for me, a lot easier for you. But are there any questions from last? Yeah.
Would the input alphabet be empty?
Yeah. So the question I raised last time was, can the input alphabet be empty? Other than the person who asked it, did anyone look that up or think about it? So I'm not just asking for asking to figure out what the answer actually is. What do you think I'm asking the question for?
So you can think about it.
So you can think about it for what reason? Because for your general knowledge and for the test. So the short answer is the book says in chapter 0 that alphabet must be non-empty. But there's nothing in the definition in chapter 1 and the one we considered that says that it must be non-empty. So the alphabet can be empty, yes. Okay. So here's another good question. If the alphabet is empty, what DFAs could exist? That's a good question to think about. Other questions? Okay, so what did we talk about last time? DFAs, right? So are those Danish French armies?
Yeah.
Yeah. Oh, yeah. So instilling revolution into 355. But what are those? What are these DFA things?
Finite automata.
Exactly. Deterministic finite automata. So what things are in DFAs that we talked about? What are the pieces of a DFA? So first off, how many pieces are there? 5. So states are one of them. What are the other parts? Alphabet.
Transition.
The transition. What is the transition thing? It's a function. It's a function because we're taking inputs from the state and the input symbol and outputting the next state. What are the other 2 pieces? Start state, because we got to know where to start the machine, and what else? We did input. The set of final states, right. So we mark some states as being final and all of the others as being not final or not accepting. So we talked about running a particular input on a machine. So we had the simple machine with just the input 0 and it goes back and forth, and basically it does, I forget which one, but even or odd number of zeros, one of those 2. So then we looked at a particular string 0, 0, 0. It must have been odd, I guess. 0, 0, 0, and we figured out, oh, it accepted that string. So we looked at, okay, we start in Q0, and then the next state is Q1, and the next state is Q0, and the last state finally is Q1. So is that formal? Is that a formal way of saying, oh, this machine computed on that string and got to this state? Is that formal? No. So we actually need to actually specify in a formal way, like the DFA definition, a formal way of saying, what does computation really mean for a machine? We can say, oh, we started in this state and we eventually ended up in this state, but how do you actually show that that is true? So, like if I tell you, okay, here's a gigantic DFA, and it does a bunch of computation, and it lands in this state over here, in some final state. I don't tell you the states in between. I just tell you, oh, you start in Q0 and you land in this state. Should you believe me? I'm the professor, so you must believe me, right? But really, should you believe me? Well, I may be telling the truth, but what should you do? Verify that it's true. Verify that we indeed do land in QF, and I'm not just telling you something that's false. So how would you verify if we have a string W with characters W1, W2, W3, up to Wn, let's say? How do you verify that we started at Q0 and correctly ended at QF? How do you verify that? Well, yeah, visually you would look at the transitions one at a time and make sure that one transition goes to a state and then the next transition you apply comes out of that state with the right symbol. So if we have like W equals 0, 1, 1, and I say that in Q0, first we apply the transition starting with 1, is that correct? No. So because we're applying the wrong transition. So we gotta write this in a formal way so that we are completely satisfied for what a computation actually is. Well, let's see. If I don't read any characters at all, so we just start the machine up and don't read anything, how many states have we seen? One, which is the start state, obviously. If we read one character only, how many states have we seen? Including repetitions, possibly. Well, we saw the start state, then we read a character and it landed at a maybe different state. So how many states have we seen? 2. If I've read n characters, how many states have we seen? N plus 1. Because 1 is for the start state, and each transition gives us a completely new state, or maybe a state from before, but we have seen n plus 1 states. So if we're going to be talking about computation, we better talk about a sequence of that many states, n plus 1, so that we start in the right place, we start in the start state correctly, and each transition is actually valid all along the way. So let's let M equal to a formal specification of some DFA. So we don't know exactly what this DFA looks like visually, because I'm just saying M is some arbitrary DFA. It has some states, some input alphabet, transition, start state, final states. But because I specified it in this way, I know for sure it's a DFA. Okay? Well, and let's let W be some string of length n. So W1, W2, up to Wn, be a member of sigma star. What is sigma star again? Yeah, all the possible strings over sigma. So all I'm saying is that it's just some string. I don't know if the DFA is going to accept it or not, but it's just some string. Okay? And I also should say where each of the individual WIs is a member of sigma. So each of the WIs here, so each of the W1, W2, W3, each one of those is a single character. So I'm not fooling you by saying, oh, well, W1 is a substring, a very long substring, and the other ones are characters. I'm saying that each one of them individually is a character, so that everything else will follow through easily. Okay, well, so a computation then of M on W so whenever I say DFA has a computation on some string W, this is what we're going to mean. Well, a computation, we could model this as the transitions that are taken, or we can model it as the states that we see along the way. So we might as well look at it from the states perspective. So is a sequence, so just a list essentially of, but it sounds cooler, a sequence of n plus 1 states Well, let's see. Do I know right now what the exact names of what the states are? Well, the first one I know, obviously, is which one? Q0. What is the next one? Is it always Q1? Well, the machine M could name all the other states anything that it wants. It can name them Arizona, Alaska, brilliant other states, right? So, anyone catch that? States? Ha 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 ha. All right. So, but could I give names to them? Maybe different names. As long as I'm just naming them, can I just name them whatever I want? Yeah. So let's name them R0, R1, R2, up to Rn. So I really have written down n plus 1 states because the 0 index on the front. Well, let's see. Could I just put period right here? It's a sequence of states. Could I write that? You can tell by my tone it isn't. Why is that not a good idea? Could I just write down any old sequence that doesn't correspond to the actual computation, the transitions that were taken? I could just write the same state over and over and over, even though that's not what the DFA might actually do. So we better make constraints on what these R states actually are. Well, let's see. Where? And we'll have two conditions. Well, what does R0 have to be no matter what the DFA is? It has to be the start state, and we called it Q0 here, because all DFAs must start in their start state, which is Q0 in this case. So R0 is equal to Q0. So far, so good. Well, can we just quit now? Well, what about all the other states? Have we made any specification on what those could be? Oh, we haven't yet. So we better make sure that the transition, I'll switch to a different color, the transition from R0 to R1 really is the first transition that we are allowed to take. The R1 to R2 transition really is the second transition that we're supposed to take. And it's the same all the way through. Okay, well, let's see. Back when we looked at an individual computation, we looked at a single character, figured out, okay, here's the state I was in before, here's the character I'm looking at, here's the resulting state. Well, how do I get R1 from R0? So R0 is the state I'm from, that's fine. What else do I need to know? The character I'm looking at. Well, what's the first character in our string? W1, okay? So to figure out R1, I need to know R0 and the first character, W1. How do I figure out R2? What two pieces of information do we need to know? What R1 is, yeah, and what else? And the second character of the input W2. Okay, well, if we're looking at the ith state, how do I figure out what two pieces of information do I need to know how to get to the ith state? Yeah.
R-1 with Wi.
Yes. So the previous state, which is Ri-1, and the ith character. Okay? So that's good. So if we know that those two bits of information, and it's true all the way through, we're all set. Well, how do I, so what place do I put those two pieces of information in, and it gives me Ri out of it? So, yeah, the transition function. So what is the transition function here called? Not theta, it's delta, right. So remember that delta takes how many arguments? How many arguments does the transition function take? 2. Oh, we conveniently have 2 bits of information. Is that a coincidence? Ah, good. I'm leading you down the garden path. So the previous state, which is Ri minus 1, and the ith character, Wi. So, but let's look at this very carefully. Am I justified in saying that it's an equality here? So the transition function outputs a state. Is the equality okay here? Yeah, because it outputs exactly one state because it's deterministic. So as long as the states are equivalent, the same state, I can put equality here. I mention this because the next model of a computation will make this modified. So it's not equal in that setting. So that's why I mentioned it. Okay, and then we got to say that this is true for every I. So for all, so I can go from 1 up to n, I think. Yeah, I think that's right. Off by 1 errors. Anyone have trouble with those? I have trouble with them too. So I believe it's I can be as small as 1 to handle the first transition and n to handle the nth transition. Okay, so a computation then is the sequence of the states that we visit so that we start correctly, which is the first one, and we follow the right transition all the way through. Cool. Any questions on what a computation actually is? Does a computation, could it land in a non-final state, just a normal computation like this? Could it land in a non-final state? Yeah, so a computation could land in a final state because there's no stipulation on what the last state in the sequence could be. So, for that reason, let's talk about an accepting computation. So an accepting computation is one where additionally, so by this we want to say that M says yes on W, actually accepts W. Well, looking at the sequence of states that we have here, how do we determine whether we said yes on this input? Well, first off, which state should be involved in that? Rn, right. So how do we determine, I'm scrolling up for a reason, how do we determine that we accept this input from Rn's perspective? Yes, if it's a member of what set? F, which is what? Set of final states. So if we have that Rn is a member of the set of final states, then we call that an accepting computation. Here's a great exam question. Hint, hint. How many computations can a DFA have on a given input? So I present you the DFA and the input. How many computations does it have? 1. Could it have more than 1? No. Why not? They're deterministic. We couldn't have a state have 2 transitions out on the same symbol, right? So, in fact, I can amend this definition to say not a sequence, the sequence. Because there's exactly one thing the DFA could do on this input. It can't stop halfway through. It has to read the whole thing. And there's no choice at any point, which is kind of nice. So there's exactly one computation for a DFA and an input. What about accepting computations? Well, for this reason, there can't be more than one accepting computation because there's only one normal computation. Could there be 0 accepting computations? Yeah. So if the DFA informally does not accept the input, it doesn't land in a final state, so it doesn't have an accepting computation. Okay? Any questions on what these two are?
You said it had zero, a DFA had 0 or 1 accepting computations?
Correct, yeah. Depending on whether it actually lands in a final state or not. But it's always one computation. Other questions? Okay, so let's define the language accepted by a DFA, let's call it M, is the set, well, it's the set W in sigma star, so all strings such that M has an accepting computation on W. And we usually denote this by L. So L is the language. Oh, that's actually not right notation. I'm going to move this over. And it's really L parentheses M. So whenever we are going to say L parentheses the machine, that's the language of that machine. So informally, this set is just the set of all strings that it accepts. So like the first example where we had all strings of odd length, the language of that machine would be all strings of odd length. Okay, so that would be an example. Yeah. So this is the language accepted by a DFA M, and we say that a language L is regular if it is accepted by some DFA. Okay, so if I assert to you that a certain language is regular, that means some DFA has that language. So let's look at some examples. What about the set of all strings? So is sigma star the set of all strings regular? In other words, is there some DFA that has that language? So basically the DFA that accepts everything, never goes to a non-final state. Yeah, how would I make it? Yeah, simply. Yeah, so just a single state like this, and it loops on everything. Everything in sigma, I guess. Can you just write it like that? Yeah, but we'll be talking about a particular sigma in pretty much every other place. This is just an arbitrary example. So, like for instance, we'll talk about sigma is equal to 0, 1 as the characters, and then you would write 0, 1 on the transition. This is just to handle all possible cases. What about the empty set? So basically the language that has nothing in it at all. So it's completely empty. So the DFA here should accept nothing. What's the language of that? Sorry, what's the DFA for that? Yeah, same idea. But instead of making the one state final, it's non-final. So here's the same thing. Let's see. Let's address a question that you might have. What about this language? So this language, is the third one here equal to the second one? No, why not? What's a simple proof of that?
Well, epsilon is an element.
Yeah, there's one element in the third one. How many elements are in the second one? 0, the empty set. So there are clearly different languages. Okay, so how would I actually do this? This one's a little more complicated. So if the string has any characters at all, I don't want to accept it. So what do we do there? Can I get away with one state? No, I don't think so. So let's see. What about the start state? Does it have to be accepting? Yeah. How would I get the empty string if the start state is not final? So the start state has to be final. So remember, we're only accepting the empty string and not accepting all of the other strings. Well, what if I have any character in the input? Should I stay in this state?
Just exit out.
Yeah, exit out of it on anything. And so I'm going to do a shorthand here by saying anything in sigma goes on this transition. And what about the state that it goes to? Should it be final? No. And what about transitions on this second state? Just stay there. So, yeah, so here are some examples of regular languages. How do you know that they're regular? Because I can make a DFA for them. What's another example of a regular language we saw last time? The very first example we did. Yeah, the strings of odd length when they're completely composed of zeros. So another example that we saw last time was, so all strings that are entirely zeros, such that the length of W is odd. What about the same language except I interchange even for odd? So even length instead of odd length. Is that one also regular? Yeah. And what's the simple proof of that? What do I do to the odd DFA to make it into the even one? Switch the final states. Huh. So let's think about that for a second. If I have a DFA and I just switch the final and non-final states, that gives me obviously another DFA. But how is the second guy's language related to the first one? It's the exact opposite. It's the complement of that language. But we're going to get to that soon. So all of these are regular because there's a DFA for them. Any questions on these? Okay, so let's see. So can anyone tell me what a language is? Just an arbitrary language. Well, it was defined to be a subset of what? No, just a language. Well, what is a language structurally? It's a set of what? The strings. But more importantly, it's a set. When you see sets, what do you want to do other than run away? What do you do with sets? Well, sets are unordered collections. What do you usually do with sets? Set operations. So what are some of them? Yeah, union, intersection, things like that. So could we do the same thing with languages that way? Because they're sets? Yeah, we can do the same. So you may be wondering, like on the homework, I have questions like W in some sigma star such that W has this property or it has this other property. Or you may say has this property and this other property. So you may be thinking, okay, well, that kind of sounds like intersection to me. If I can solve the two pieces individually, if I know how to do intersection for DFAs, could I do it easily here? Could I solve this whole problem, this property and this property, that way, if I know how to do intersection? Yeah, because that's what intersection is. It's a member of this set and of this set. Okay? So let's talk about operations. So let's let C be a class of languages. So you may not know this term class, but it's basically, you have a bunch of languages. So maybe C is the set of regular languages, or any other languages you want, or all languages, whatever you want. So we say that C is closed under an operation. I'm going to do a plus with a circle around it, just to denote some arbitrary operation. So we say that this class of languages is closed under an operation, whatever it is, if applying it to languages in C in this class has the result also in C. So by this, if we can prove, for example, the class of regular languages is closed under union, what that means informally is pick any two regular languages you want, their union is also regular. Okay? So there's no chance, if it's closed under some operation, that applying it gets you outside of that class. Okay? We like regular languages because the model for them is very simple. So if we can prove that some operations are have the regular languages closed under them, then we can actually say a lot about how to make bigger and bigger problems for DFAs. So we can just work with small pieces and then figure out how to combine these pieces to solve the original problem. So if we have some property and some other property, you just work on the individual pieces and then just apply some algorithm to put them together, which is pretty cool. So let's see. What are some operations? So let's talk about something called the regular operations. So you may think, okay, they're called regular operations, therefore the regular languages are closed under them. Is that true? Just because they're called regular, does that have anything to do with regular language? So this is one of the sad things of this area, is that we'll have, I believe, 4 different uses of the word regular in this class. I'm not kidding. So, and this is the second one. So just because it's called regular, don't immediately associate that with the DFA, the regular languages are closed under these. Okay, so there are 3 operations here. So the first one is union. So union, all it is if we have 2 languages, A and B, then the union A union B, as you might expect, is the set of all W's, all the strings W, such that W is in A or W is in B. So this is just normal union, nothing special here. Okay? Any questions on union? Okay. So we're going to completely blow your mind with the next 2. So the next one is concatenation. So in normal programming, what is concatenation? Take a string here, take another string here. What does concatenation do? Glues them together with super glue. So it's the exact same idea here. So so we have, again, languages A and B. So the way we write concatenation of the languages themselves is just we put the names of the languages together. Sometimes we put a little circle in the middle. You'll see that sometimes if you look in the literature. But the way we're going to do it is just we're going to stick them together. So what is this? So this is all the strings WX, so literally putting these two strings together such that the first one, W, comes from A, and the second one, X, comes from B. So all this really is intuitively is that we have two languages, A and B. Pick any string you want out of A, pick any string you want out of B, stick them together in that order, okay? So as an example, let's consider A equal to 0, 1, and B equal to 2, 3. So what is A concatenated with B equal to in this case? So pick any string out of the first one, A. 0 is fine. Pick any one out of B. 2. Put them together in that order, A first, with 0, 2. So is 2, 0 a member of A concatenated with B? No, good. So it has to be in the right order. And the other ones are 0, 3, 1, 2, and 1, 3. Okay? Any questions on concat? Because we're going to need it for the third one. So we talked about sigma star. What was sigma star again? Yeah, all possible strings over sigma. Is that formal? Saying all strings over sigma? Not really. So let's actually formally define star. So this is actually called clean or cleany star. So here we're going to only have a single language A. So, and we write the star of A as A star. Not like the search algorithm for AI, but it just happened to work this time. So A star is equal to this. So it's the union, and I'll explain it when we're done. The union over all k at least 0 of A to the k. So what in the hell did I just write? So what did I actually write? Can anyone explain? Yeah.
You can have an infinitely long string.
Ooh, I wouldn't say that.
Okay. Or up to whatever k is.
Yeah, so pick any integer, positive integer k, and then what?
And then that will be the length.
Yeah, so let's actually define what A to the k actually means. So A to the 0, well, how do I pick 0 strings out of A? What is the only string that I can pick 0 of? Empty string. So A to the 0 is just the set containing the empty string. And A to the k in the general case is the concatenation of A with k minus 1 for k at least 1. So this means that pick any k that you want. This means that we're picking something from A, and then let's just say k is 2, for example. So we pick something from A, and then we pick maybe a different string from A, then glue those together. If I picked k equal to 4, then I pick 4 strings of A, maybe different, maybe the same, and then I glue all of them together in that order, whatever order I pick them. So what is an example here? So let's do 0, 1, 0 star. So what is a guaranteed element of this star right here? Always. What is always in there? The empty string. So that's always in there. So if A itself is the empty set, well, A to the 0 always is defined to be the set containing the empty string. So that string is always there. Maybe other ones are there, but empty string is always there. So empty is in there. Now, what are all the ways that I can pick something from this set 0, 1, 0 exactly once? Exactly one string from there in all possible ways. Well, how many strings are in here? 2. So there are 2 ways that I can pick one string from it. And those 2 possibilities are 0 and 1, 0. So those are the 2 possibilities. Now, what are the ways that I can pick 2 strings from this language? Well, could I pick 0 twice? Yeah, as long as I pick some string in the language twice, I'm all set. So 0, 0's in there. Well, could I pick 0 and then 1, 0 afterwards? Yeah, so the resulting string is 0, 1, 0. What about the other way? I pick 1, 0 first, and then I pick 0. What is the resulting string? 1, 0, 0. Good. And then if I picked 1, 0 twice, there's only one way to do that. And we can continue on for eternity doing that. So it's all ways we can pick certain strings from a set. The way that we've seen it with sigma star so far is that everything in sigma has exactly one character in it. So it's effectively just saying all the strings over this set. But we're defining it more generally here because a language could have strings more than one character long. Okay? But are there any questions about that? About what star actually is? A question, yeah.
So a star operation on any set will give you a set with infinitely many.
Oh, great question. Is a star always infinite? Well, let's see. If it has a string of any non-zero length, so not just epsilon, but some other string, is it going to be infinite? Yeah, why? Yeah, I can always pick that string. So pick it once, then pick it twice, then pick it 3 times, then pick it 4 times, etc. Are all of those strings going to be different from each other? Or are we just going to get the same string many times? Well, it has non-zero length. So if I keep adding it onto the existing string, am I going to get a longer string every time? Ah, so therefore, I'm going to get infinitely many strings out of that. So if A has any string of non-zero length, then A star is infinite. That could be an AI slogan, I think. A star is infinite. But anyway, A star is infinite if you have any string of non-zero length. Cool. So what are the possibilities if it doesn't have a string of non-zero length? Just the empty string is one possibility. So if we have that case, what is just this set star? Well, what is in the star of any language? Not empty set. Empty string, good. So empty string's in there. Is anything else in there? Well, what if I take the empty string, concatenate it with itself? What string do I get out of it? Empty string. Notice why I asked that question, do we get new strings every time? Because here, we don't. If you concatenate the empty string with itself, I'm going to get the same string over and over and over. So is there anything else in this set? No. So that's the set. So it's not always true that the star of any language is infinite. But is this the only possibility? If it doesn't have any string of non-zero length, is this set right here the only possibility?
No.
What's the other possibility?
The queen star of the null set.
Of the empty set, right. So empty set star. What is in the star of any language again? Empty string's always in there. Is there anything else in this set? No, let's see. Concatenate any string in the empty set with itself. Well, let's see. This is precisely, by definition, union empty set, because that's just the language. Union empty set concatenated with itself. Union doing this 3 times, etc. Well, what is a set union the empty set yield you? The original set itself. It's like adding 0. You don't change the number, you're just getting the original number back. Here we're getting the original set back. So we're getting just the empty set out of this. Cool. So it's not always true that A star is infinite. Most of the time it is, but these 2 cases prove that it isn't. Okay, cool. Any questions on this otherwise? I think that's a good time to have a break, and we'll come back on more of this stuff.